Alright, so it should be Thursday, and let's start off with you guys doing a homework check on number 3. 10 points for doing, 5 points for checking. And then, Miss Stedman, if you could please pause the video if they end up having questions on homework. And today's notes aren't too long, so if you need about maybe 10 minutes to go over homework, you should have 10, maybe 15 total um, to go over that. All right, otherwise, let's get started. All right, so let's just start off with some older concepts, and then from there we will jump into what we're doing today. So to start off, let's look at area as an integral. So let's just take some function, and if I ask you to find the area bounded between there and the x-axis, we essentially find these representative rectangles. This is my dx, the height is f of x, and we end up finding the area as an integral because we do the integral from a to b of the height times dx, dx being the width, which really ends up equaling, and I'm running out of space in my nice little box there, a to b of f of x times dx. And then, same exact concept, I really want you to think about the fact that a height is one dimension. You're going to multiply it by another dimension. So now we're going to talk about volume. Same function, f of x. And how do we make a volume? Well, we're going to make volumes many different ways, okay? Today, we're going to focus on shapes kind of popping out at you. Seems a little crazy. It'll be hard to imagine, but I want to discuss just the concept of how you would use, and this is supposed to say volume, how you're going to end up using an integral to find volume. Well, let's talk a little bit about area. We found area by finding the integral from a to b of a height multiplied by dx. Well, I'm going to give you a clue about volume. You're going to do an integral from a to b, and you're still going to multiply by dx. And what I said a second ago was that's one dimension multiplied by another dimension. So that height, let's use real units. Inches multiplied by inches give us the area of inches squared. Well, if this was inches, what would you have to multiply to get a volume being inches cubed? Well, logically, you need inches squared. So you're actually going to be taking an area, multiplying it by dx to get a volume. That'll give you areas are squared units, multiplied by another unit gives you cubic units. So that's the basic concept, but the more important thing is whose area do you find? Well, let's take this function here and trying to think if I want to draw something on here or try to do a different one. Let's take this function and let's build squares that pop out at you. Now, Mr. Ish is amazing at this. I am not. So here is a height, but now I'm going to turn it into a square. And then the next one, oh god, this is going to look horrible, would be, let's say here. So they are horribly ugly and definitely not what I want it to be, but I'm going to just kind of at least show you a concept. I want you to see that the volume, the area that we're going to end up talking about is something called a cross section. And that's what these squares are representing, is some type of cross section. I'm actually going to go back and delete that for a second and say to you, Ms. Stedman, in the math office, hopefully you got it. You would have gotten the diagrams that the girls and my aides all made for me so that you can kind of show them what cross sections look like. But to describe a cross section, I'm going to have to use this guy. So here's a function, and we're going to create a cross section that's squares. So what I mean by that is, given a function, you're going to create length. We're going to make this 3D, so we're going to drop that down. And I'm going to show you what squares look like, much better than the crappy graph I just made. So there are 4 squares. What I want you to see is that if you take the squares and go along the curve, it changes the size of the square. But that square that you're looking at is what we call a cross-section. Now, I'm going to stop it. I'm going to show you what this solid would look like. Now, I am horrible at drawing these, which is why I'm using this program. I'm hoping you're all oohing and eyeing. Here's what that solid looks like. It's made from squares. And if I was to slice down parallel to the y-axis, perpendicular to the x-axis, you would see a bunch of squares. So I just wanted you to at least see a picture of what it looks like, because I can't draw them. Some of you would probably draw them way better than me. So let's kind of go back to the notes and look at the concept. And the concept being that you're going to take a volume by doing the integral from a to b of the area of the cross section, that's what cs stands for, dx. And honestly, we are going to do some that are dy. Okay? So let's start off with how we're going to do this. The first thing you're going to figure out is your integral a and b values. Actually, let's not do that first. First thing I want you to do is figure out, is it a dx problem or a dy problem? And the way that we know this is if we end up doing our shapes. So these are perpendicular to the x-axis, and these are perpendicular to the y-axis. That's the first thing. Second thing, find the area of the cross-section. Formula. We'll talk about that in a second. 3, you're going to use the function in the area formula. And then lastly, I'm going to do that down here. You'll do that the volume is equal to a to b integral of the area of cross-section multiplied by dx. All right, so let's use what we just have written down. And we're going to start by writing down some formulas that will be extremely helpful for you. Let's start off with the area of a triangle. Easy, 1/2 base times height. Area of a square, side squared. Put parentheses around the s, please. Area of a rectangle, and actually do that for all of these. Base times height. Area of a circle, pi r squared. An area of an equilateral triangle. Let's draw that out. Okay, so call that the side of an equilateral triangle. I'm going to drop a height down. You should realize that all the angles of the triangle, 60 degrees. And if this whole thing is s, then this whole thing over here is also s. And there is a relationship, 30, 60, 90 relationship, which I'll put over here for you. If this is a, this would be a root 3, and this would be 2a. So if this is my s is supposed to be my 2a, then that would make a 1/2 s. Therefore, to find the height of the triangle, a is 1/2 s multiplied by root 3. So putting that all together, the area of an equilateral triangle is 1/2 base. The whole base is s all the way across. The height, which we just found, I'm going to clean that up a little bit. Root 3 over 2 times s. Simplify that a little bit more, and we get root 3 over 4 s squared. And if you memorize the formula, it's helpful. If you don't memorize it, you do have to use a little bit of the 30, 60, 90. You can also do it by using the sine, cosine, SOHCAHTOA. All right? So we're going to end up using these formulas. So these are the formulas that you're going to use to find the area of your cross-section. So I'm actually going to skip Number, actually, no, we're not going to skip number 1. Let's do this. You're going to end up doing a lot more revolution type problems later, but I think we should be able to do this problem. So let's start off with drawing out the function. That's always helpful. Going to 1, we're going from -2 to +2, and we are going to do, oh, that is horrible looking. Let me draw that much nicer, please. All right, there we go. All right, so from -2 to +2. If I want a pretty accurate graph, we're going to substitute in the values, and you get -2, 17 and +17 for both. So, and then it's not going to be the best looking graph. It's not going to be the prettiest thing, but there you go. All right, so we're going to actually revolve this around the x-axis. So I'm going to show you the easiest way to figure out what it looks like. You're going to reflect the shape across the x-axis, and then you're going to give yourself these 2 circles that connect top and bottom. So it kind of looks like a sideways vase, maybe? I don't really know. But there you go. So that's kind of what it looks like. So let's talk about the cross-section. You should be able to see it pretty well. The cross-sections are circles. Okay? Now that you have a circle, we're going to do this volume. First thing we're going to figure out is, number 1, is it a dx or a dy problem? And if you look, the circle is perpendicular to the x-axis, therefore it's a dx problem. So step 1, I know it's a dx. Now that I know it's a dx problem, I'm going to need x values for everything. So let's start off with volume is equal to, my x values would go from -2 to +2. I know I'm going to be doing the cross-section of a circle, and it's a dx problem. So that's where I start. In terms of finding the circle, we always start off with writing a formula. Write out the formula of what you want. So in this case, I'm going to need to find the radius. So let's erase this a little bit so I have some extra room. I'm going to actually show you what the radius looks like in red. If I have this circle here, the radius would be this line. If I have this circle here, the radius would be this line. If I have, do in black, a circle here, the radius would be this line. Now in terms of that line, I pretty much look at that line and I say, well, how would I find the height of that line? What you should notice is, if we were doing anything with rectangles, the height of that line would be the top part of the line minus the bottom part of the line. The other way you could think of it, wouldn't the purple function, which is 4x squared plus 1, that would give us the height of that line. If this y value here, or this y value here, or this y value here, will give us the height of that black radius, and that's the radius of each circle. So the radius of the circles change, but they're changing because of this function up here. So how would I rewrite the volume? We go from -2 to 2. Volume would be 4x squared plus 1 is my radius, squared dx. So this is the radius. So we're going to take the same function. We're going to do different types of areas. So let's do the same graph again. Oh, Lord. My graphs are ugly. So from now on, hope that I don't even know if that's anywhere close to symmetric. All right, so there is my graph. It said that we're going from -2 to 2. Draw a little line down. Wow, that's not even close. All right, so 2. All right, so that's what we have. We want cross sections that are perpendicular to the x-axis. So I don't actually physically draw out the whole square. As you can see, the reason is because I can't draw them very well. I just draw the base of the square. So there's a base of a square. There's a base of a square. There's a base of a square. And just by doing that, I can figure out that that's supposed to be the square. You want to take a look, you can kind of draw one popping out at you. Okay? those are the squares popping out at you. In that case, first of all, we know that they're perpendicular to the x-axis, so I know this is the x problem. And I know I'm using a square, so that's the formula for a square. So any problem you get, you should always write the area formula first. Secondly, you just have to figure out the side with reference to the function that they gave us. Well, this function, y equal to 4x squared plus 1, isn't that the height of this line, which is the base of the square. So I know that negative 2 to 2, I would be able to find the, oh sorry, wow, I didn't notice that. Find the volume of a shape whose squares bases are perpendicular to the x-axis and are made from the line y equal to 4x squared plus 1. All right, let's look at the next one. Rectangles. So we're still using the same function, okay? Why I did not copy that shape over, I do not know. All right, and there we go. So I know I'm going to stop here and here, that's negative 2 to 2. And now I want rectangular cross sections where the height is 3 times the base. Well, the base is sitting inside of the shape. The height of the rectangle is going to be 3 times the base. So this is the base, this is 3 times b. Okay? So, volume, first of all, perpendicular to the x-axis, tells me it's a dx problem. A rectangle's area is base times height. That is exactly what I start out with. Secondly, the height was 3b. So now I write in 3b. And why I keep writing dx, I have no idea. I'm sorry, dy. Then I simplify it. And to do that, I'm actually going to move this up a little bit. Oh, Lord. I'm apparently not. And I have no idea why I have an equal sign there. All right, so let's simplify it. Negative 2 to 2 of 3b squared dx. So I just need to figure out what b is, because I'm going to put the 3 and then the b squared dx. By now you should have figured out the base, still the height of the shape. That is the reason why we get to put that in there. Okay? Number 4, isosceles triangles where the base is perpendicular to the x-axis. I was supposed to give a little bit more information than just the fact that it's an isosceles triangle. When you get these problems, there will always be enough information to understand them fully. Oopsie. So, negative 2 to 2. So, isosceles triangle. Oh, I did give enough information. I'm kidding. It's an isosceles right triangle. So, you are going to be given either that the base is perpendicular to the x-axis, or you'll be given that the hypotenuse is inside of the shape. In this case, because it's the base, this is the base of the triangle. And, oh, Lord, the other base would be here, and then this would be the right angle. Wow, that's horrible. So really, what you're looking at is a triangle that looks like this. It's isosceles. This is the base. This is the other base. Therefore, the volume would be equal to negative 2 to 2, because we are going perpendicular to the x-axis, 1/2 base times height. And the height is also base. So I'm going to simplify this. Oh, Lord. 1/2 b squared dx. So I just have to figure out what b is. Same problem setup, so hopefully you have figured out now that the 1/2 we can even put outside, but that the base is the height, which is the same as what we've been doing for every single problem. All right, so I'm just essentially getting you to practice using each of the formulas. Okay, semicircles, for some reason, always an issue. All right, so instead of like the first one where we rotated, created full circles, we're only going to create a semicircle. So if this is the perpendicular to the x-axis, this is what it looks like. Now, a semicircle volume from -2 to 2, we know that this is a dx problem because we're perpendicular to the x-axis. Semicircle would be 1/2 pi r squared. So let's start off with a few things. If you want that pi, 1/2 pi out of the way, you can move it. Because now you realize you only need that r. Now the radius is not this whole piece. That's the diameter. We need the radius. We only want half of it. So I would need half of the 4x squared plus 1. That's the radius. 1/2 the height, and the height was 4x plus 1. That's what's in here. All right. Make sure you understand this is because it's a semicircle. This radius is why there's a half sitting there. Okay? And this right here is the whole diameter. All right. Equilateral triangles. Miss Stedman, if you could have them try this one on their own, if you could press pause. So, if most of you guys are done, you should have had that the volume is equal to -2 to 2 equilateral triangles from before. We had √3 over 4 s squared. We're perpendicular to the x-axis. You should have had √3 over 4 times 4x squared plus 1 squared dx. All right. So now I am not going to do this problem because I think I actually messed this up. That was not the question I wanted to ask. All right, so this one is a little bit better. Now we're going to go perpendicular to the x-axis. I added a little bit extra information, or sorry, y-axis. I added that we're in the first quadrant. So now we're only using one side of the graph. Okay. And we are going to do, and the x-axis over the interval from -3 to 2. That totally makes no sense whatsoever. All right, let's try to fix this guy. We're going to bound between the y-axis over the interval and x equal to 2. So those are the new bounds. I'm really sorry. I think I have a bunch of typos in this problem. So we want to do y equal to 17 is what I'm supposed to be using here. Sorry about this. Y equal to 17. Sorry. All right. So now that makes a little bit more sense. So we're using the function y equals 4x squared plus 1. We're using the function y equal to 17 and the y-axis. So, oh Lord, we will be bounding y equal to 17 would be here. So this is the piece that I want to bound. Then let's use this to make squares that are perpendicular to the y-axis. So all I do is I just draw one, okay? Now that's the base of the square. You should realize that the square then comes out at you, okay? You don't need that piece. I usually don't even draw that. I have enough information just from that to tell me, well, my volume would be, these have to now be y values because I'm doing a dy problem because we're perpendicular to the y-axis. Given that, I still know I'm doing squares. So first thing, let's look at the y values. You should be able to tell, remember that was y equal to 1, and that's y equal to 17. So that's 1, and that's 17. Secondly, I need to know how big this is. Well, we're in terms of y, so that's an issue. I'm going to come over here, and let's do this function in terms of y would mean I have to solve for x. So I get y minus 1 over 4 is equal to x squared, and then x is equal to plus or minus the square root of y minus 1 over 4. How do I know if it's positive or negative? You look at the y values that you have. All those y values are positive, so I'm only using the plus side. Therefore, this right here is the function x is equal to the square root of y minus 1 over 4. Now, if you think about when we did area, you think about right and left, you can see that the right function would be the x, and then the left function 0. So if you are having a little bit of trouble because it got turned on its side, you're still using the same concept that you used when you did area. You can essentially use big minus small to always find height or the length that you need. So in this case, I would end up using that x is the root of y minus 1 over 4, and that is the side. I'm going to square it, dy. I'll be honest, it's now really late and I'm exhausted, so I may be doing a pretty not so awesome job of explaining this, especially with the pictures that I'm giving. So, Ms. Stedman, if you need to pause, redo some things here, because I don't know if you guys are understanding as well as I would want you to. It is not fun having to teach you through video and not being there. So I really apologize for making the mistake on this problem, and hopefully that you do somewhat understand the basic concept of a volume is going to be the integral of an area times dx or dy. The perpendicular to always tells you which, if it's going to be a dx or a dy function, or sorry, integral, and then from there, you're always using an area formula. To find volume. All right.